When SpaceX's Starship lifts off, most people watch the rocket, and that's the wrong place to look. The structure left standing behind it, a 146-meter steel tower nicknamed Mechazilla, is, by SpaceX CEO Elon Musk's own assessment, as complex and difficult as either the booster or the ship. And understanding why that name exists changes how you see modern spaceflight entirely. Every kilogram a rocket carries to orbit burns fuel just by existing, and engineers have a name for this problem: the tyranny of the rocket equation. SpaceX already knew this with Falcon 9, a rocket that lands on 4 deployable legs, adding several hundred kilograms to the booster on every single flight. On a vehicle that size, that's a manageable cost. But Super Heavy, the first stage of Starship, standing 71 meters tall and generating over 16 million pounds of thrust, changes the math entirely, because at that scale, hundreds of extra kilograms of landing hardware become a genuinely prohibitive weight penalty on every mission. Musk's answer was to refuse the trade, strip the legs off the rocket and put the complexity on the ground instead. At the February 2022 Starbase presentation, standing in front of the first fully stocked Starship, he put it plainly: the tower and the launch system, which I call Stage 0, is really as important as Stage 1 or Stage 2. The Orbital Launch and Integration Tower, the OLIT, doesn't just hold the rocket before launch. It participates actively in every phase of the mission. And the first thing it does before a single engine fires is serve as the rocket's crane. SpaceX chose not to install a traditional crane at the top of the tower, and the 2 giant catch arms, the chopsticks as workers call them, fill that role instead, capable of lifting the 50-meter Starship upper stage and placing it precisely on top of the Super Heavy booster, even in the high Gulf Coast winds that are almost constant at Boca Chica. Each arm runs about 36 meters from tip to power, which is roughly 120 feet, and they're mounted on a carriage that travels up and down the tower's exterior on tracks, guided by 12 steel guide blocks along 3 of the 4 tower legs. What's unusual about the drive system is where the power lives, not at the top, but at the base, where a winch and spool connects via cable to a pulley at the tower's peak, keeping the heavy machinery accessible and serviceable at ground level. The weight debt logic becomes clear here. SpaceX traded the simplicity of legs bolted to the rocket, no external dependency, for a ground system of real mechanical complexity. And the bet is that complexity sitting on the ground, where it can be maintained and upgraded without touching the vehicle, is better than mass that must be launched and recovered on every flight. Whether that bet pays off at scale is the central question of the entire Starship program, and the first evidence arrived on October 13, 2024. At 7:25 a.m. on October 13, 2024, Starship's 5th integrated flight test lifted off from Starbase, and 7 minutes later, the Super Heavy booster came back. What followed has been called, without much exaggeration, one of the most significant milestones in spaceflight history. The booster descended with 13 engines initially firing to begin the landing burn, throttling down to just 3 for the final approach, its position correcting continuously as it lined up with the open chopstick arms. The arms closed, the rocket stopped. It hung in the air above the same pad it had left minutes before, held in place by steel. The physics of what they just pulled off deserves a closer look. Super Heavy carries a dry mass of around 200 metric tons, far beyond Falcon 9's roughly 25-ton landing weight. And the arms had to close around a vehicle that was still under thrust, still correcting its own position autonomously, descending into a gap measured in meters. Catch pins on the booster's interstage, positioned between the grid fins, serve as the interface point for the arms, and getting those pins to arrive at the right position on a vehicle returning from near supersonic speeds, guided by onboard computers coordinating with ground systems in real time, has no precedent anywhere in aerospace history. Before the flight, Musk had put the odds with characteristic directness. The probability is uncertain, but it is above 0. By the end of 2025, Mechazilla had caught Super Heavy boosters on 3 separate flights: IFT-5 in October 2024, IFT-7 in January 2025, and IFT-8 in March 2025. And what had once been called an audacious gamble had become a repeatable procedure.
Booster reuse followed on IFT-9 in May 2025, when Booster 14 flew for the second time on 29 previously flown Raptor engines, marking another step in the program's progression. The arms were designed as a stacking tool and became a recovery system, with their capital cost serving both functions simultaneously, and that dual-use design is central to why Stage Zero's complexity is considered worth building in the first place.
The catch arms attract attention, but the engineering layer beneath them, largely invisible to cameras, may be the more demanding problem. Starship and Super Heavy burn liquid oxygen and liquid methane, both stored at cryogenic temperatures far below the freezing point of water. The Starbase tank farm holds roughly 4,950 metric tons of liquid oxygen, 1,420 metric tons of liquid methane, and 2,710 metric tons of liquid nitrogen, and a single orbital launch consumes approximately 3,760 metric tons of liquid oxygen and 1,040 metric tons of methane, meaning the farm holds barely enough for one mission with margin to spare. Filling those tanks as of the early operational period required around 400 tanker truck deliveries per launch campaign, often sourced from facilities more than 500 miles away. SpaceX began construction of an on-site air separation unit to produce liquid oxygen and liquid nitrogen directly at Starbase through cryogenic distillation, while industrial gas company Linde builds a separate $100 million plant in nearby Brownsville, expected online in 2026. Cutting delivery distances from over 500 miles to under 50. The propellants don't flow straight into the rocket from storage. They pass through subcoolers that use liquid nitrogen temperatures to chill them further, increasing density and packing more energy per unit volume into the vehicle, then travel through a ground support equipment bunker before reaching the launch table and the tower itself. That launch table, a custom-built structure weighing 370 metric tons, contains its own quick disconnect system delivering fuel, pressure and gases, and electrical connections to Super Heavy up to the moment of liftoff, when 20 clamps release simultaneously. The tower's quick disconnect arm handles the upper stage separately, swinging out to connect to Starship's umbilical panel on the hull exterior before each flight and retracting before ignition. Routing Starship's connections through an external tower arm rather than through the booster was a significant design shift that happened mid-development, chosen as part of the broader push to keep complexity off the vehicle and on the ground. The physical machinery of Mechazilla only functions because of a software and sensor infrastructure operating on millisecond timescales, and this layer of Stage Zero receives the least coverage despite being what transforms the tower from steel and pipes into a system capable of catching a rocket. Consider the booster return sequence in detail. After stage separation, Super Heavy performs a boost backburn to redirect its velocity toward the pad, then re-enters the atmosphere, decelerating from supersonic speeds. During the final descent, the landing burn begins, 13 center engines firing first to arrest the drop rate, then throttling to 3 for the approach, while the booster's guidance algorithms adjust continuously and onboard computers coordinate in real time with ground systems at Starbase. None of that coordination is passive. The arms need to be positioned at the correct height on the carriage and at the correct horizontal extension before the booster arrives, and that positioning depends on live telemetry from the descending vehicle. An automated flight safety system on the ground independently monitors the trajectory the entire time, retaining authority to redirect the booster to a water splashdown if the approach falls outside acceptable limits, a decision that must resolve before the vehicle commits to the pad, which means the logic runs on automated systems, not human reaction time. The quick disconnect arm runs its own software protocol during propellant loading, monitoring temperatures, pressures, and flow rates across a sensor network embedded throughout the cryogenic plumbing. All the complexity described in the previous 4 sections exists for one reason, and that reason hasn't been fully demonstrated yet, but it's the reason the whole system was designed this way. Falcon 9's turnaround from landing to relaunch runs in weeks to months.
The booster touches down on a drone ship at sea or at a land-based landing zone, then gets transported back to the launch site, inspected, refurbished, and eventually restocked with a new upper stage before flying again. That logistics chain involves horizontal transport, vertical integration, and extensive between-flight processing at every step. Mechazilla was designed to collapse that chain towards something closer to the turnaround time of a commercial aircraft. The booster lands on the tower, already at the launch site, held by the same arms that will restock it for the next mission, with cryogenic loading infrastructure already connected and the QD arm already present. Musk's stated aspiration is to enable a booster relaunch within under an hour of landing, with an eventual goal of launching the same Starship vehicle 3 times a day from a single pad. Numbers that aren't engineering claims about current capability, but about what the architecture is designed to make possible. SpaceX is building around this model at pace. A $250 million Gigabuy facility broke ground at Starbase in July 2025, with completion targeted for December 2026, designed to support manufacturing and refurbishment of up to 1,000 Starship vehicles per year by end of decade.